Right. The most recent thing that we did in math was solving one and two step variable equations. Um, that's something that a few of the kids were pretty familiar with already. I kind of have the feeling that you might be in that boat too, but I'm going to walk you through the full demonstration I did for them just to make sure you're squared away and that, when you come back you can have had the same observations and the same lesson as everyone else. But we just wrapped this up. So what you see in front of you is not typically used for math. It's usually used in science. It's called a balance scale or a pan balance. And what that does for us is it doesn't necessarily have to tell you an exact weight of something. But what it does do is it allows you to make a comparison. So right now, there's nothing in either side. So it stays balanced, it stays level. It's not, skewed one way or the other. If I put something in one side and I put something in the opposite side, well, the quick and easy observation is we have no idea how much that rock I just put in there weighs, but we can say with certainty that it weighs more than this little wooden cube, just based on the fact that it sank to the side. So the reason we have this out is because it has everything to do with the equal sign. In most of our experiences in math, an equal sign is just going to tell you the truth about something. It's going to tell you that without a doubt, 3 plus 2 equals 5. The equal sign's only going to state a fact. And if this were not true, if 3 plus 2 didn't equal 5, that equal sign couldn't be there. Well, it's the same way in a variable equation. The equal sign won't always tell us the exact value of something, but what it will tell us is a truth that what is on the left and what is on the right side are balanced. And as soon as we do something to a variable equation that changes one side of it or the other, we need to make sure that that we don't turn that equal sign into a lie about it. The equal sign, the scale, will always tell us the truth when it comes to comparing two things. Now, it's going to be a little bit inexact because I'm using things like those wooden cubes and school supplies. But let me show you what I'm talking about. So it's a variable equation that, for example, I could take that marker that I was just using and 1, 2, 3, 4 cubes. And so right now, I have no idea how much that marker weighs. And honestly, I don't know how much the cubes weigh either, because we're not really trying to find an exact value. We're trying to make a comparison. So right now, I know that the markers and 4 cubes are about to be equal to something. Let's see what they balance out with. 1, 2, 3, 4. And it jumped a little, so I know I'm close. 5. And like I said, it's not going to be exactly balanced because we're working with school supplies. I'm going to lean that way. That's a separate science lesson for another day about levers and fulcrums. So right now I'm looking at this, and we'll pretend that it's perfectly flat and level. I've got a marker, and I've got 4 cubes on this side, and then I put 5 on this side. So right now, if your math is solid, if your fact family comprehension is solid, like I know it is, you could make a pretty quick observation about this. Here's the observation that you could make. I don't know what the marker is worth, but I know that when I put it with 4, it balances out with this 5. Anytime we're working on a variable equation, our goal is to get this variable by itself on one side of the equal sign and get only numbers on the other side. And it has everything to do with fact families, the way we do that. So I said my goal was to get the marker, to get the variable by itself on this side. The way I'm going to do that is I'm going to take out those 4 cubes. I've got the marker by itself now. So I took out those 4 cubes. I've got a positive 4, and I took away 4. So that's going to cancel out. I did what I wanted. I've got the marker by itself now, but here's the problem. I told you at the very beginning that we didn't want to do anything that turned this scale, that turned this equal sign into a lie. Well, right now, the scale is not balanced. The equal sign is not true. The reason why is because we took a balanced situation and I lightened the load on this side, and suddenly this side sank down to the bottom. I've got to balance it back out, make it true again. The way I do that, I took 4 away on the left side. I have to take 4 away on the right side as well. So I took 4 away. I've got 1 left. Again, not perfect, but close enough for you to see, the example I'm trying to give. It balances back out. So what does that tell us? Well, I took away 4 on this side. I had to take away 4 on this side as well. 5 minus 4 gives you 1. We went from a situation where all we were doing was making a comparison, and we whittle it down to where we've got the variable alone on one side and only a number left on the other side, and we get that marker was equal to 1 of the cubes. How do we prove that? Well, we can prove that by plugging the variable, or swapping the variable out with our new number. So I'm going to take the same situation, but instead of saying m plus 4 equals 5, I take that 1 plus 4, and I'm pretty sure you know that that's always going to equal 5. So it won't always be that simple, but if you've got your head wrapped around fact families, it's going to be a breeze for you to do this, I promise. So let me show you something else. Let me show you got a pack of crayons, and I'm going to put them together with 5 cubes. So right now, I have no idea how much those crayons are going to weigh or how much they're going to be worth. All I can do is make a comparison. So I'm going to put in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So, not perfect, but a balance scale is pretty fickle. You can see that it's close enough to make the comparison work. So right now, I still don't have a solid idea of how much these crayons are worth, but what I do know is that when I take that package of crayons and I put them together with 5 cubes, it balances out, or close enough. It balances out with 12 cubes. So I can do the same thing that I did before, where I'm going to do what I can to get these crayons by themselves on this side. And so what can I do to undo the plus 5? Well, I'm going to take 5 away. 5 minus 5, that's going to leave me with only the crayons on this side. So I'm going to take those 5 out. Only crayons left, but the problem is my equal sign's not true anymore. I still have 12 over there, and all of a sudden it's skewing heavy to that side. So what do? Well, I took 5 away on this side. I have to do the exact same thing on the other side to make my equal sign true again. So that's 3, 4, 5. Close enough. So I took away 5 on that side. Close enough back to balanced. 12 minus 5 gives us 7. So that tells us that the package of crayons was worth 7 of those cubes. It's going to work the same way no matter what the operation is. I wish I could show you with this scale what subtraction looked like over here, but it doesn't really work in the demonstration. But it is the exact same idea, where I could take something like, the variable x. I don't know how much it's worth, but what I do know is that when I have x and I take away 8, I'm left with 3. My goal in any variable equation is to get that variable by itself. It's not alone right now. It's stuck with the -8. So I'm going to do what I can to shuffle around the sides of the equal sign, to shuffle around my pan balance, and I'm going to get this variable by itself. So the way I'm going to do that is I'm going to do the opposite of the -8, and I'm going to add 8. I can't just do it to this side. It's got to happen on the other side as well. Otherwise, my scale's untrue. It's off balance. My equal sign is not true anymore. So I've got a -8 and I add 8 to it. It cancels out and I'm left with only the variable. So all that's left is to do the 3 plus 8 and I get 11. To prove it, take this and plug it back in. Where I used to have x, I'm going to substitute in 11. And I'm just going to make sure it's true. Is 11 minus 8 equal to 3? And I sure hope that, even though you've been gone for a while, I hope you haven't forgotten that 11 minus 8 is 3. So you're good. It works the same way with multiplication and division. So I'm going to show you one like that. So the way I do that is, still using school supplies. Instead of using, one package of crayons or one marker, we're going to go with 3 pairs of scissors. I don't know how much those 3 altogether are equal. I don't know how much one of those pairs of scissors is worth. But I know that when I take 3 pairs of scissors and I put them together with 4 of these cubes, that it balances out with 2, 4, 6, 8, 10 cubes. Or at least it did earlier. Again, that's a science lesson for another day on why I'm trying to move those to the other side. So just do me a favor and pretend that's a little more balanced than it actually is right now. It's not quite sunk all the way to the bottom. Just call it even, all right? So I've got 3 pairs of scissors. I'm going to call a pair of scissors S because, scissors. How many do I have? I have 3 of them. So I could say I have 3 times the weight of those scissors. But the problem with this is once we're dealing with variables, we get into this awkward situation where I don't want to have anything that looks like 2 variables. You'll get there in math someday where you're dealing with multiple variables. Right now, this looks like a mess. So I can't have 3 multiplication symbol x, s. So I'm going to do something a little bit different, and you're going to have to flash back to that PEMDAS lesson with parentheses, where it's understood anytime you've got a number butted up next to the parentheses, it means multiplication. Anytime you've got a number butted right up next to a variable, it means multiplication. How many s's? 3 of them. 3s. So I've got 3s, and then I put 4 of those cubes in there with it. And it balanced out with 10 cubes. I'm still going to do the same thing I did before. My goal is to get this variable by itself. With this sort of situation, you want to do the easiest thing first, basically. We can't worry about getting this 3 detached from this s, because that's just a messy situation of division. So we're going to do what we did before. We're going to start off by undoing the addition. How do we undo addition? Well, I'm going to take those 4 blocks out. I'm going to do the same thing on this side. I'm going to take 4 blocks away, but here's the difference. So I take 4 blocks out from that side and from this side as well. So, like you see, we're back to balanced. We're back to good for the most part with our scale, but we still don't have what we were looking for. We do have 3 pairs of scissors on this side, and we've chopped it down to where that's going to be balanced with 6 cubes. That still doesn't tell me what I wanted to know, which was, well, how much is that S worth? So I've got another step to do. It's not going to be any different than the addition and subtraction were. Whatever the operation is, whatever's got the variable stuck with something else, I have to undo it by doing the opposite. What's the opposite of multiplication? It's division. And like I said at the very beginning, if you've got your brain wrapped around fact families, you already know the answer to this. So we read this, I see 3 times something is going to be equal to 6. Well, what's the fact family flip of that? The fact family flip of that is undo this multiplication by dividing. Do the same on the other side. So our fact family flip is 3 times something equals 6. 6 divided by 3 equals something. This cancels out because 3 divided by 3 is 1. So all I have left is an S on this side. 1 pair of scissors. 6 divided by 3 is always going to be 2. So I'm going to take this out. I'm going to leave 2 in there, and hopefully that balances out and shows you that 1 pair of scissors is about the same as 2 cubes. That's about as difficult as it gets. The only other thing that I can show you is that division and multiplication work the same way, flipped around. So I could have something like, 12 divided by z equals 6. This one's a little bit different. This one's about as tricky as it's going to get. And it's going to require us to do some flipping back and forth. Like I said, as long as you've got your head wrapped around fact families, you're fine. I never realized how much my 2's looked like z's until they were next to each other. So I want this variable by itself. Right now it's stuck with 12 divided by that z. If you've got your head wrapped around fact families, I know I keep saying that, but that's how I taught the lesson to everybody else. If you understand fact families, you already know the answer to this question. 12 divided by something equals 6. Well, how do we undo division? We do the opposite and we multiply. So I'm going to multiply this side times z. I have to do the same thing on this side. The division and the multiplication are going to cancel each other out. So all I'm left with on this side is 12. And I see that that's equal to, still don't know what z is, but I know when I take 6 and I multiply it by z, it's going to be equal to 12. Then I do exactly what we did on the last problem. 6 is stuck to that z because they're being multiplied together. I want to break that bond. I want to break that multiplication by dividing both sides by 6. 6 divided by 6, that's 1. So all I'm left with is a z on this side. 12 divided by 6 is 2. You probably knew this a long time ago because you know that 12 divided by 2 does equal 6. That's about as tricky as it gets. So let me show you one or two problems from the homework sheet. I just looked at this and it told me that I've been filming for 20 minutes. If you don't watch this, I'm going to be so sad. But, man, I really do have a feeling that you probably already understand this kind of thing. And if you don't, I know that you'll get it very quickly. So on this sheet 8.3, problem number 1 is C divided by 5 equals 13. A lot of kids get nervous about seeing variables pop up, but really, tell yourself to read it differently. Something divided by 5 equals 13. You know fact families. So you know that I can multiply both sides times 5. This cancels out. I'm left with C. C is equal to whatever 13 times 5 is. 65. How can we prove it? Fact families. Something divided by 5 equals 13. 13 times 5 equals our something. And then we just plug it back in. 65 divided by 5 equals 13. Is it true? Yep. And none of these are any different at all. No different at all. I'm trying to look and see if I can find one that's going to be trickier than that. And man, I'm really not seeing anything. They did what I told you that they shouldn't do. That should be that dot, just to be clear. So I've got, don't know how much F is worth, but I know that F times 4 is equal to 92. So I'm going to divide both of those sides by 4. That leaves me with, well, 4 divided by 4 is 1. So all I've got here is F. I've got to figure out what 92 divided by 4 is. 23. The proof, 92 is equal to 23 times 4. I just plug it back into where it was. Word problems are no trickier. The only thing that I kept telling everybody was a lot like the PEMDAS problems. If you need to, draw it out. Draw a simple picture just to wrap your head around it, to clarify, what exactly is it asking you. A school district purchased 90 new computers. The computers were divided equally among 6 classrooms. How many new computers are in each classroom? In your equation, let C represent the number of computers in each classroom. Here's the other thing about variable equations. You've been solving these since probably about the 3rd grade. As soon as you started getting multiplication and division word problems, you had variable problems. So to me, honestly, it's a little bit silly that they want to turn this into a variable equation because, well, take a look at what's going on here. They purchased 90 new computers. So I'm not going to draw out 90 computers, but I'm going to draw, a couple little boxes. These are my computers. They're old school desktops. What happened to these? Well, they got split out to 6 classes. Okay, so this class gets some, this class, this class, this class, this class. Well, doesn't that look pretty familiar? You take a large number and you split it into smaller groups. It looks a lot like division to me. And that's why I was saying that this is kind of silly, because you don't necessarily need a variable to solve this, but I'll show you how it does play in. So it's just like any division problem you ever did. 90 computers split into 6 classes. That would be 90 divided by 6. Well, and they want you to use C. That's going to equal C, the number of computers in each class. Well, if I took that C away and I left you 90 divided by 6 equals blank, how long have you been solving problems like that? Long time. But it says, in your equation, let C represent the number of computers in each classroom. So the way you do that, I could do it just the flip, the fact family opposite of it. 90 computers divided into groups of C, because I don't know how many computers go in each class. But I know that that's how many will go into 6 classes. And it works either way. That number 15, write a real world problem for the equation 4 times y equals 60. You know, you know exactly what to do with that because we did that a long time ago. I think it involved a lot of laughing about wrecking balls. I'm not too concerned about you with any of this stuff. Like I said, if it wasn't already familiar to you, you're going to wrap your head around it very quickly. Email me back. Let me know if you have any questions about this. The attachments for these documents are in the email. Take a look at some of the problems. Don't feel like you need to do all of them because they're pretty repetitive. If you understood what happened on the board and what happened with those examples, for 5th grade, it doesn't get any more difficult than that. Like I said, email me if you have any questions. I hope I hope your trip wraps up well. I hope your grandfather's doing well. Let me know if you need anything, and I will talk to you soon.